So welcome all of you for the second lecture on matter waves, the so-called de Broglie waves. And after this, what we shall do is to look at the various models for atom. We will first of all make precise what we mean by an atom, because that word itself has undergone a change in its meaning. And then we will discuss some crucial experiments which supports what is called as the planetary model of the atom. But before getting on to the atomic model, we have to first conclude our discussion on matter waves by looking at one very important aspect of matter waves. Because as you people know, no study of any wave phenomenon is complete unless we establish a relation between frequency, wavelength and velocity. So you have frequency, you have wavelength, you have velocity, and this of course is well known by elementary arguments that V is given by nu lambda. However, it is not as simple as it seems to be, because these are not ordinary frequencies and ordinary wavelengths that we have for the usual waves, but the frequencies and the wavelengths are inferred from two other physical quantities. Remember, in waves, the energy carried by the wave is always proportional to the square of the amplitude. So we say a person is speaking louder, a person is speaking softer, or an instrument is being hit very hard. What we are worried about is not the frequency or the wavelength, but the amplitude, how high the amplitude is. So for example, if you have a percussion like tabla or mridangam or whatever, drums, so harder you hit, larger will be the amplitude of vibrations, and that is what is going to contribute to the energy. However, when we come to the description of light as a photon or matter as a wave, de Broglie wave, we are doing something which is counter to whatever we have discussed in the case of classical waves, whether it is classical electromagnetic radiation or sound waves for that matter. What we are doing is to associate frequency with energy. So we are saying E equal to h nu. That is the statement that we are making, and we are associating a wavelength with momentum. So we are writing lambda equal to h by p. Now these relations are quite harmless when we consider light. That is something that I want to tell you, and I already discussed that in my previous lecture. Because what is going to happen is that we have a fundamental relation U equal to Pc for an electromagnetic wave. Let us say we have monochromatic plane wave, then it is easy to show that U equal to Pc. A better way of representing it is U equal to pi c. So let us discard this expression, where U is the energy density and pi is my momentum density. Where do I get these expressions? I get these expressions from classical electromagnetic wave picture of Maxwell. That is something that you have to do. But if I combine this with the Planck idea, so what is it that is going to happen? So my U, as I told you in my last lecture, is nothing but n into h into nu. I am assuming that the radiation has only one frequency, and this n is my number density. And what is my pi? My pi is the same number density into the momentum carried by each of the photon. That is the most important thing. H nu is the energy carried by the individual photon, and P is again the energy carried by the individual photon. And what are we writing? We are saying this quantity is nothing but U by C, NH nu by C. That is what we are writing. So now if I am going to compare this with the standard definition of the wavelength, there is absolutely no conflict at all. Okay, if you want, you can even write this as n into P is h by lambda. That is what you are going to get. So if you combine these two relations, you will get the well-known relation my C equal to nu lambda. So when it comes to the concept of a photon, it is in complete consonance, it is in complete agreement with the natural notion of a wave, where the speed is product of the frequency and the wavelength. So it is some kind of a self-consistent picture. It is a self-consistent picture insofar as this equation is concerned, but it is really not self-consistent from the viewpoint of fundamental physics, because we are, without any care or without any botheration, we are mixing up concepts of waves, concepts of particles in order to get these relations. But still, even within that limited notion of consistency, we are able to see that there is no conflict. But when it comes to massive particles, that was for radiation, when it comes to massive particles, situation change. Massive particles means de Broglie waves. So before I do that, I would like to direct your attention to this slide, the Davis and Germer experiment. So this is the great experiment which they performed in 1927. And what are we finding? We find that there are beautiful peaks which correspond to constructive interference. That is what we are finding here. So what we are saying is that Davis and Germer experiment establishes consistency waves n lambda equal to 2d sin theta. I already argued how this equation comes about in the previous lecture, provided, that is the most important thing, the results agree with this, provided we assign lambda to be equal to h by p. Remember, what they had was an electron gun which shot off electrons. It could be something like a thermoelectric emitter or some such thing. You pass current or you heat it and it produces it ionizes the electron. Then it was accelerated through a certain voltage. It kept on gaining momentum. Now the particles with this known momentum are impinging on my nickel crystal, but the scattering results can be understood if I associate a lambda with this p through this relation. In other words, p is what is known and lambda is what is associated. This in fact is the great contribution or the great intuition of de Broglie when he proposed this hypothesis. Now we are going to encounter a rather peculiar situation, because you have the momentum, you have the energy coming from the particle, and then you have the nu, and you have the wave number, the wavelength, which is going to correspond to the wave picture. So for the same entity, let me call it as an entity, electron in this particular case, when I look upon it as a particle, I am associating a momentum and I am associating an energy which is given by Newton, because these are essentially non-relativistic particles. Their velocities are very small compared to the speed of light. But when I am looking at it from the viewpoint of so-called quantum picture, the old quantum theory, I am associating a frequency nu and a wavelength with them. Now you see, there are two notions of velocity. What are the two notions of velocity that I have? One notion is I will write p equal to mv, and I will write e equal to half mv squared, let us say, or I can write it as p squared by 2m. So I can put a vector sign here also. So there is one velocity which is coming because of the standard dynamics notions which you people studied in your 11th standard. So this is one particular picture. The other picture is that what is given by v equal to nu lambda. That is what we have. What we have found in my previous pages was that as far as light is concerned, whether you look at the speed of light from the viewpoint of a photon or the speed of light from the viewpoint of a wave, they are going to agree. So v, it always turned out to be c irrespective of whether you looked at it as a collection of photons or whether you looked upon it as a wave. But what we do not know is whether the same thing holds. So what I am trying to tell you is that we have two notions, the velocity of a particle and the other one is velocity of a wave, and the question is, do they agree with each other? I do not want to provide an answer to this question in this lecture. Rather, what I would like you to show is that this is a rather unpleasant thing to encounter at this particular point, but there is a very definite answer, and I would leave it to you people to actually figure out how it comes about. As I was mentioning in my last lecture, what is required is actually the notion of a group velocity, which we have not studied so far. But when we are teaching or when we are studying a subject like matter waves or photon as matter, it is good for us to be alive to these issues. Otherwise, everything would be appearing to be simpler than what it is. That is the most important thing. So now, therefore, let me analyze what is going to happen. You have two concepts, E equal to h nu, which is equal to p squared by 2m. It turns out that when people write down the relation between the frequency and the wavelength, etc., it is customary not to employ this frequency or the wavelength, but it is customary to employ a different frequency which you people are all familiar with, and that is angular frequency. In a similar manner, what people would like to employ when they are looking at the counterpart of the wavelength is not wavelength. So my nu is replaced by omega purely for, it is a matter of convention. My lambda goes to k, and this is what is called as a wave number. My lambda goes to k, and that is what is called as a wave number. So how do I write my energy? I write my energy to be h nu. And what is the relation between omega and nu? Omega equal to 2 pi nu. Therefore, this quantity is h into omega by 2 pi. That is what we have. And there is a very, very special notation for this h by 2 pi, and this is identically equal to h bar omega. So most of the time, actually in physics, later when you study more and more of quantum physics or even electromagnetic theory, when we speak of frequency, most of the time we speak of the angular frequency omega rather than the usual frequency. There is no great difference between them except for a factor of 2 pi. So let me record it. My omega is nothing but 2 pi nu. That is what it is. In a similar manner, we wrote the relation P equal to h by lambda. So what I am going to now do is to replace h by h bar. So remember, h bar is h by 2 pi. Therefore, I am going to write it as, so h bar is h by 2 pi. Therefore, h is 2 pi h bar by lambda. That is what I have. So you people should know that h bar is a more commonly used quantity rather than the original Planck constant itself. And if I write it as h bar into 2 pi by lambda, this is identically denoted as h bar k. So k has the dimension of inverse wavelength. It is called the wave number. So the standard notation is that you describe the wave properties in terms of the frequency, the angular frequency omega, and the wave number k. So what would be the relation between omega and k vis-a-vis c? When we wrote it in terms of nu and lambda, we wrote v equal to nu lambda. The same relation becomes omega equal to ck. So this is the standard way we represent the relation between the angular frequency of the photon, the wave number of the photon, and the speed of light. And this relation is what is called as a dispersion relation. So what is this telling us? This is telling us that as you keep on changing your wave number, that is, as you keep on changing the momentum of the photon, my omega also keeps changing, that is, the energy also keeps on changing, such that the speed is always the same. Irrespective of what your frequencies are, irrespective of what your wavelength is, all frequencies travel with the same speed equal to c in free space. That is the statement that we are making, and essentially Einstein made use of it to propound this principle of relativity by saying that it is not only the same in one inertial frame, but every other inertial frame, all possible inertial frames. So this is a dispersion relation. At this point, actually, we can take a detour and ask what would happen if I were to get into a medium. If I were to get into a medium, then the speed would change, because in a medium, k would change to k prime, omega will remain the same, therefore my c would be different, so this becomes a c of k prime. And that is the reason why when there is a refraction of white light in a medium, let us say in glass or water or whatever, different frequencies travel with different velocities, they get bent at different angles, and on the right side you see the different colors that you are going to see. That is a famous case of dispersion, and this explains why you make use of the word dispersion relation. At this point, of course, you should know it is not very important for us to use omega and k. I just introduced it to you because it is some kind of a convention, although in your 12th standard you may not use it. So now what we do is to return to matter waves. Let us return to the matter waves. So basically, these are the questions that we have raised. So let us reiterate. We are asking that given the fact that momentum fixes the wavelength, what fixes the energy, and then what is the relation between frequency, wavelength and the speed. So when we speak of the speed, we have two different varieties of speed, different kinds of speed. One is the speed of the wave and another is the speed of the particle. This question is very, very important, and it occupied de Broglie himself quite a lot, because he gave a model called the pilot wave, because we have to explain how a particle can have a wave-like behavior. It is easy to explain how a wave can behave like a particle, because we can say wave is an extended object, therefore lot of particles join together and behave as if they are a wave. But a particle is a highly localized object. It is a point particle for all practical purposes. What do you mean by associating a wave? It is a very, very important question that we have to ask ourselves, and that is the reason why I have listed these three questions. And although they are not technically a part of your syllabus, it is very important for us to ponder over this. So what do we have? I have lambda equal to h by p, and I have nu is equal to E by h, because h nu is equal to E. Now what I am going to do is to first consider non-relativistic case. So in the non-relativistic case, we all know the relation between energy and momentum. My energy is simply given by p squared by 2m. Energy is simply given by p squared by 2m. So I can play a game. What I can do is I can multiply lambda into nu. That would be the speed with which the wave would move. So this is the matter wave, this is the matter frequency. I am assigning this m. So I am going to write lambda m nu m, and this would be the velocity of the de Broglie wave. De Broglie wave. And what is this quantity? This quantity is nothing but h will cancel E by p. This quantity is nothing but E by p. So what are we saying? We are saying that the speed with which a de Broglie wave moves from the fundamental notions of wave phenomena is simply given by E by p. And this is going to be bothersome to us. So let me repeat. V matter wave is equal to lambda, same thing, let me call it as mw into nu mw, which we found to be E by P. And what is E? E is given by half mv squared, P is given by mv. Of course, it has the correct dimension of velocity, but if we calculate this, what are we going to get? We are going to get v by 2. That is what we are going to get. And what is this v? This v is of the particle. So what we are saying is that if you imagine that the particle is moving with a velocity v, then there is a certain wave associated with it. That is what de Broglie is saying. It is not entirely a figment of imagination, because the great experiment of Davison and Germer has shown that there is some meaning to that. Because although they are particles, when they hit the 111 phase of nickel crystal and when they got reflected, you had to use ray optics, you had to find out the path difference, you had to find the phase difference, and you found there is a constructive interference which only waves can exhibit, which particles cannot exhibit. That is why Davison and Germer were rather astonished. And now we are saying when the particle is moving, this poor wave cannot keep track of it, cannot run with the same speed. So this is the particle speed, and my wave speed is given by v by 2. It is lagging behind. So if you naively use your known notions of velocity, frequency, etc., you land into trouble. Although it worked out in the case of light, you see that it is not going to work out in the case of matter waves. So that is one thing to worry about. Now of course, there is a great distinction between what you do in the case of light and what you do in the case of, let us say, non-relativistic particles. We know that light is essentially quote unquote relativistic in the sense that nobody can enter the rest frame of light, because it moves with the same speed with respect to all inertial frames. You people have certainly heard of that in your popular lectures in relativity. So it may occur to us that what we should be doing is not use the non-relativistic expression, but we should use the relativistic expression. Then perhaps everything will be fine, and then I will take a limit. So this was Newtonian. Now what I will do is I will use the relativistic expression and see what I will get. So we look at relativistic de Broglie waves, matter waves. Let us look at that. My fundamental relations are still intact. E equal to h nu, P equal to h by lambda. That is what I have. Maybe again I should write nu equal to E by h, lambda equal to h by p. Therefore, my nu, as in the earlier case, is given by E by p. I am repeating this calculation because it is worthwhile to have this kind of redundancy so that the idea gets completely fixed. Except that now for E and P I am not going to employ Newtonian expression, but I will employ relativistic expression. So what is my energy? My energy is given by m naught c squared over root of 1 minus v squared by c squared. This is your relativistic energy. In fact, you are going to use it quite a lot when you study nuclear physics, mass defect and all those phenomena. So you have that. And my momentum is nothing but, so let me write here, my momentum is mv over root of 1 minus v squared by c squared. I will put an m naught because I have to remember it as a rest mass. So if I did that, it is good to write it in this one. I made a mistake, so I should correct myself. My lambda nu is given by E by P, which is the velocity. So I have corrected myself here. So I am going to substitute for E by P. E by P. And what are we saying? We are saying E equal to m naught c squared over root of 1 minus v squared by c squared, and P is equal to m naught v over root of 1 minus v squared by c squared. Of course, I am not writing any vectorial sign at this particular point because I am assuming that all the particles are moving in the same direction. We do not have to worry about that. So, what is my E by P? Let us calculate that. So, my V wave, what is this quantity? So, I am looking at this expression, m naught cancels, the gamma factor 1 over root 1 minus v squared by c squared cancels. I get an even more fantastic expression, namely the speed with which the wave moves is given by c squared by v. This v is the particle velocity. If you look at the expression for this momentum goes to infinity when v goes to c, which means no material particle, no particle which has a rest mass can move with a speed equal to c, let alone with a speed greater than c. That is why we say speed of light is the maximum speed. Nobody can ever achieve that. No material particle can achieve that. So that means my v is always less than c. So what are we finding? We are finding that v wave is always greater than c. There is only one exception to this rule, and that is when my propagating particle, quote unquote particle, is not a classical particle but a photon itself. Then my photon is moving with a speed c, I get c squared by c. So that is how you reconcile with the electromagnetic result. Therefore, although Davison and Germer experiment tells us, there is something called a matter wave, it is going to get diffracted, there is going to be an interference between two different layers, and then you are going to see maxima whenever n lambda equal to 2d sin theta. That must be understood more carefully, because in one case my matter wave was not able to catch up with my particle, and in another case my matter wave is running far ahead. In fact, it is running with superluminal speed, which is impossible. Okay? So these are the two questions which you have to ponder about, think deeply about. The clue to the answer to this question is actually found in what is called as group velocity. I will not discuss that, but I would like you people to keep this in mind. Okay. So this concludes the study of the so-called matter waves. You have all the standard problems now. Given the wavelength, find the momentum. Given the energy, find the frequency. Or given the momentum, find the wavelength, so on and so forth. They are not of great interest, although they would be of interest to calculate, because that will give you a rough idea of what the de Broglie wavelengths are, things like that. But all these studies, the study of the concept of a photon or a matter wave, raises an even more fundamental question. So remember, what we are now doing is to look at particles which are incredibly small and which are impossible to see with the naked eye. So for example, when people first discovered the cathode rays or the anode rays, so on and so forth, they appeared like rays, and it was only very, very careful measurements that revealed that they have a particle-like nature, that electrons are particles. Is that okay? And now we have confounded the notions of wave and a particle. Is that okay? So basically what these studies do is to essentially raise a fundamental question: what are the fundamental constituents of matter? Is matter continuous? Is matter discrete? Is the fundamental constituent a wave? Is the fundamental constituent a particle? Because we have seen a particle can behave like a wave can behave like a particle. So this takes us back to the great question which the human beings posed thousands of years ago: what are the fundamental constituents of matter? And this is what leads us to the famous Bohr model. But then when we speak of the Bohr model, what we are actually doing is to jump over a few thousand years. So what I will now do is to start with the notion of an atom. So we have essentially made a transition to the next topic, the Bohr model, but the Bohr model will come a little bit late. We have to do a lot of preliminary work for that. So look upon this as a second lecture in this series. What we have is to worry about the structure of the atom. So let us have some preliminary discussions. So all the matter that we see around us are what we call as gross matter, and we can actually break. You can even break stone. Diamond is a very hard material, but diamond will be polished and cut by other diamonds. And of course, whether it is wood or plastic or any other material you can break. We know that mountains are formed, mountains break, mountains actually lose soil because of continuous erosion, so on and so forth. So that means we know that all the objects that we see around us are actually made of finer particles. There is no question about that. So you take a sugar crystal, you take salt crystal, or you take anything, you can actually crush it into a powder. You can take wood and you can crush it into a powder. So the big question that people have asked, philosophers, scientists, they have asked, is that what are the ultimate constituents? Now, when I speak of ultimate constituents of matter, there are two things that we have to worry about. Those ultimate constituents must be somehow become perceptible to me. I must be able to feel them. I cannot say that matter is made of an ultimate constituent which nobody can ever know anything about. Then that is a useless statement. There may be a very large number of links, but eventually it may be related to, it should be related to the way I am going to observe them. That is one very important notion. And another, of course, is that when I speak of an ultimate constituent of matter, is it possible that I can keep on making finer and finer and there is no end to it at all? So it is like a mathematics question. So what do? You give me two numbers, I will always produce a number in between them. A is a number, B is a number, A plus B by 2 lies in between them. Now take that number and let us say you take B, there is another number between them, there is no end to this limit. In fact, the whole real line is a continuous line, so other possibility is that matter is continuum. So whether matter is continuum or whether matter it is discrete is a different matter. But if you take it from the viewpoint that eventually all kinds of matter, if they have to be understood by me, have to be related to me through observation in some manner, we ask ourselves, how do we observe? You may build the most sophisticated instrument, but ultimately you get to know it either through your eyes or through your nose or your ears or your sense of touch or your sense of taste. So when we look at the second one, other schools, the great elements, these are called the Mahabhutas in India, right? People argued that there must be an underlying quality which is responsible for my sense of touch, sense of sight, sense of hearing, sense of smelling, and all these five attributes, and these entities were given names. These are the great five elements which they call earth, water, fire, air and ether. Ether does not particularly exist in Greece, they spoke of only 4 elements, but in India they also introduced the concept corresponding to ether, not exactly ether, that is what was called as Akasha. So what you essentially say is that when I see this piece of wood, or when I see you, or when I touch this, there is a certain quality inherent in me corresponding to the touch. There is a quality inherent in that corresponding to touch, and that is the reason why there is a certain knowledge that is accruing. This is not a humdrum idea, it is not a useless idea, because after all we say, if I want to know that there is an electric field, I need an electric charge. After all, the charge produces its own electric field. If I want to know that there is a gravitational field, I need a mass, because after all, the mass produces its own gravitational field. So that was the idea. So people postulated the existence of these great elements are the Mahabhutas. These are the great elements out of which everything has been constituted. At this point, you should not confuse words like earth, water, fire, air or Akasha to be the earth that we see, the water that we touch or the fire that we feel. No, that is not what it means. These were simply the names given. Basically you are saying earth has a preponderance of that quality, water has a preponderance of this quality. It is not, doesn't mean that the element itself is earth, that the element is water or fire or anything. You simply pick up names from ordinary words and you are calling them. That is something that you have to remember. Now the question is, given these great elements, they may be there, they may not be there, is there a continuum or no continuum? The schools were divided, but today for us the most attractive school is the school which propagated the atomic theory of matter, because we believe that matter is discrete and it is not continuous. However, when these ideas were postulated thousands of years ago, there was no evidence either way. So in India, for example, when we speak of the great elements, they are found in the Upanishads. Probably they were composed 1000 BC or 1500 BC, so it is that ancient. Whereas the later philosophical school, we have 6 schools of philosophy. One of them is what is called as the Vaisheshika school, where they try to classify all matter known to us. They postulated the existence of a fundamental unit of matter, and that was called Anu. So I should write that here. The Indian school of atomism. The founder of the school was Kanada. So we have to be careful. If I write Kanada, it can give rise to confusion. So we write in Devanagari so that there is no confusion about it at all. And there is an interesting pun about his name, because the word Kan means a particle. Okay. So Ada means to eat. It seems that he kept on consuming small particles of food or whatever. So obviously this must be some kind of a euphemism, some name given to him, because he propagated the atomic theory. But technically the fundamental units were called Anus. And that is the name we have actually used today in order to describe an atom. So in today's chemistry book or physics book, if you look at the Hindi version, an atom is called Anu and a nucleus is called Paramanu, probably. So that is what we have. Actually sometimes it is also called, nucleus is also called Nabhikiya. We will not worry about that. The technical word is Anu, and it was believed that there are many kinds of atoms. Is that okay? So let us establish a correspondence with the idea of the Greek school, who called atom. Atom is a unit, Anu is a unit. So in Greece it was Democritus, as we saw, and the combination of these atoms is what gives rise to the visible matter. So there were these detailed questions about as to when it becomes visible. So one school said that you need a minimum of 3 atoms to join together in order to become visible to the naked eye. Obviously all these were speculations, but they had a certain element of novelty, a certain element of ingenuity in them, because eventually people wanted to trace back all the ordinary activities around us to something fundamental. That is what we have. Of course, all these had absolutely no evidence coming from either observation or experiment. They were purely speculative. So if we go from, let us say, hundreds of years before Christ, and we come back to more recent Middle Ages, the great proponents of atomic theory, of course, probably were in England. Dalton, I suppose, was a Britisher. The great proponent was Isaac Newton and Dalton. So Newton wrote a very famous book called Principles of Mathematical Philosophy, Principia Mathematica, where he gave all the laws of mechanics and discussed gravitation. But Newton was not only great in mechanics, dynamics, but he also made fundamental contribution to optics. After all, he fabricated his own lens. Probably he made a first reflecting telescopes on and so forth. So in his book on optics, at the end, Newton actually posed 31 questions, queries. He raised a number of questions on the nature of matter, because Newton was not only doing physics, but he was also in touch with lot of alchemists. So there was, I think, Lavoisier in France, and there were other people in England, and the alchemists are the people who actually gave us the idea of an element and a molecule. He was in touch with them. So he started speculating on the ultimate constituents of matter. So if you students get time, actually you should try to read all the 31 questions that he has posed. They are amazing. So he asked questions like, is it not possible that if a ray of light comes very close to matter, it will start bending? So he had anticipated what Einstein demonstrated 300 years later, that is the gravitational bending of light. So in a similar manner he asked, we know that in order to break a piece of wood, for example, you would require certain energy, but to break the smaller piece of wood, it will require more and more energy. As it becomes smaller and smaller, the particles that bind them will become harder and harder, and he asked, is it not possible that you will reach an ultimate limit where you have these small spherical balls which are completely microscopic, let us say, which are infinitely hard, and they were all created by the great God himself, and they are combining to be ordinary matter, and they must be indestructible. So the whole idea of an atom is that it is indestructible. Nobody can ever destroy them, nobody can ever modify them. So that was the great idea of Newton. As I told you, I have already discussed the other schools. But the real evidence for the existence of an atom actually did not come from physics in the sense, we do mechanics or whatever. It really came from people who do chemistry and thermodynamics. Chemists were great people. I think Priestley is the person who separated hydrogen for the first time. Lavoisier was able to get oxygen for the first time. People realized water was actually a composite of hydrogen and atom. People were able to find out. Then of course Dalton came and gave his theory of ideal gas, etc., etc. Then people found out that many of the molecules that we see around could be actually understood in terms of the combination of more elementary quantities. These are your famous elements, and eventually Mendeleev came and gave us the periodic table. Of course there were a lot of missing things, but people were able to make a distinction between an element and a molecule. Element is more primary than a molecule. Now the question is, what is the fundamental unit of an element? So we have a rather nebulous, vague idea of an atom is, but the great work of these chemists actually sharpened that idea. So now we say, when we speak of an atom, we are asking for a fundamental unit of an element. What is an element? An element is that which is an elementary constituent of a chemical reaction. In order to understand any chemical reaction, you have to start with elements, and then you can go to molecules, supermolecules, bigger molecules, macromolecules, so on and so on and so forth. But elements themselves will not be understood in the language of chemical reactions. They are the basic quantities that enter. Then of course there was thermodynamics. People were studying thermodynamics, people were studying gases. You people have studied that, and all of you have encountered a very famous number called the Avogadro number. There are so many molecules. That was another fillip that came from thermodynamics. And moreover, in the end of the 19th century, there were these great experiments started with Becquerel and then continued by Marie and Pierre Curie. They were the husband and wife couple, where they found that there was something called radioactivity that was going on, and it is because of which the well-known alpha rays, beta rays, gamma rays were observed. But for whatever reason, in your course you are going to study radioactivity not before atomic model but later, but never mind, when you do nuclear physics. So all these gave credence to the idea that there is a fundamental entity called an atom simply because of the elements. That is the most important thing. So now we are able to give a rigorous definition of what we mean by an atom. Therefore, when we speak of an atom in the 21st century, or for that matter even in the 20th century, these atoms should not be confused with the notion of an atom which either Kanada or Democritus had. There is no point in comparing the two, just as the notion of a graha in Indian astronomy should not be confused with the modern notion of a planet. These are technical words which are used in entirely different contexts. So we can read whatever is written in this slide. We say atoms are fundamental units of chemical reaction. If I give that definition, now it is an operational definition. There is a consequence. We do not know whether they are ultimate constituents of matter, whether they are not. If they are ultimate constituents of matter, you cannot break them. If they are not, then you can probably break them. And moreover, if they are ultimate constituents of matter, if they are in some sense they must be so small that you should not be able to see their size, or otherwise I should be able to find out what the structure of these atoms is. This is the most important thing, and this is where models for the atoms come. So when I speak of the models of the atom, you should understand that because of radioactivity, because of the neutrality, people had figured out an atom contains both positive and negative charges. So the negative charges are of course the electrons, which were discovered by Thomson, and then the positive charges were known. So because after all in the periodic table you start saying there are these electrons, although you don't know the shell model, but these are the quantities that are contributing. In fact, I have not made a slide here. There was a cubic model of an atom by the chemists where they used to place the electrons at different vertices of a cube. If two vertices joined, they called it a single bond. If two lines joined, they called it a double bond, so on and so forth. So there were such models also. We are not going to discuss them, but we are going to look at two very major contenders. One is the plum pudding model, which was proposed by Thomson, and another is the planetary model proposed by Rutherford. The first figure that you see, you can see is Democritus at 460 BC, Dalton in 1803 AD. Okay, and if you speak of Kanada, probably he was somewhere in the 1st century AD or whatever, we don't know what the time is, I don't remember that. They thought of atoms as impenetrable hard spheres. So that is what you have. Okay, of course I am confusing the two words, but it doesn't harm us because that cartoon is there. The Thomson model imagined that an atom is what? A uniform distribution of positive charge. So that is your some fruit. So that is the plum pudding model. Okay, and inside those yellow lines that you see, they are actually negative charge particles. They are all so distributed such that the whole system is stable, and then of course it behaves as a single entity. Today we know there is a serious problem with this kind of a picture, because when you people study electrodynamics in your next year, when you go for engineering or pure sciences, you will see that it is impossible to have a stable equilibrium by static charges. Okay, an atom would not be stable, it will come apart. Even the slightest disturbance would actually break away the atom. At that point they did not worry too much, or probably Thomson imagined these electrons are all going round and round in an atom or whatever. So this was the picture. The picture that is most appealing is actually that of Rutherford, because unlike Thomson and Democritus, which was based on mere intuition or speculation, Rutherford model actually came because of an experiment, and that is what we are going to discuss next. And reconciliation of Rutherford model with classical mechanics, because it was in conflict with the laws of classical mechanics, gave rise to the Bohr model. So that is what you have. So ignore the last two ones, please stop at the Rutherford model. Bohr model is also a correct description, but the quantum cloud model is a completely misleading description. We should be very careful about that, although chemists know how to use it in a very nice fashion. So what we have to now do is to actually look at the experimental basis for modeling a what? For modeling an atom. And remember, atom is a fundamental unit of an element, and the element that Rutherford chose in order to probe its structure was none other than gold. It was a thin gold foil. So that is what we want to discuss. So this picture is taken from Encyclopedia Britannica. I hope you people will be able to see this. So what did Mr. Rutherford do? This is a path-breaking experiment in the world of physics, and we should remember that Bohr was actually Rutherford's disciple. He was sitting in Rutherford's lab when he was making Bohr model and formulating Bohr model. So what Rutherford did was to realize that the so-called alpha particles, everyone knew that it was carrying 2 units of charge, electron charge with a positive sign, they would be emitted by radioactive material. So the radioactive material that he chose was actually bismuth. So probably I have the next slide. Let me describe that, and then let me come to the description of the apparatus. So he took this radioactive source, 214 bismuth 83. So in modern language, it has 83 electrons, and the number of protons and neutrons is 214. So that means there are 83 protons and the rest are all neutrons. That is something that we should remember, that the number of neutrons is in large excess over the number of protons. In fact, it is more than twice. That is what you have. So he took the source. I don't remember what the half-life is. Let us not worry about that. And these produce alpha particles of energy 5.5 million electron volts. So now we are speaking of really large energies, and I want to spend quite some time playing around with that energy, if not today but in the next class. The target was a very thin gold foil. A foil is a very thin sheet. So a good example of such a foil probably would be the sliver of silver which we see on our sweets. It is a very thin layer, right? You can actually not peel it at all. It is stuck to the sweet. It is a very thin layer. So How thin was it? The thickness was as small as 2.1 into 10 to the power of minus 7 meters. That is what it was. Then of course the detector was a zinc sulfide, which was a scintillating object. So every time an alpha particle or a charged particle hits it, it scintillates. So you know where the scattered alpha particle has hit. So he had a microscope through which he would see that, and he would record the number of alpha particles that are scattered by this gold foil. So all these numbers are taken from your NCERT book. So you can go them and look them up. Rutherford was fortunately a careful person, because by that time people had understood how dangerous radiation from radioactive sources are. So initially, actually, when radioactivity was discovered, people thought that because radioactive materials glow because they also emit light in the visible range, people thought it will be very nice. And initially these radioactive materials were mixed with paints, and they were used for whitewashing houses because it would give a nice glowing color. It was done particularly in Germany and probably in France. And one person who worked extensively on radioactivity and got a Nobel Prize, Marie Curie, actually got so badly affected by radioactivity, she developed cancer. But by the time of Rutherford, people knew how to do experiments more carefully. So you see, he has put a source and has put a thick lead shield so that the observer is outside. And lead is a very, very good absorber of radioactivity, so that means you are reasonably safe. And that is what they do when you go, for example, for your X-ray and all that. They put a shield. Is that okay? That is what it is. He made a thin hole and the beam of alpha particles goes. You want an even better collimation, so he put another lead shield and made a small hole, okay, because the lead absorb whatever falls outside will be there. And there was the thin gold foil, and it is shown in golden color in the picture. That is what he did. So probably I can show it here in the cursor, not that it matters. And then what you have is a rotatable, so that is what is shown in the green lines, rotatable zinc sulfide detectors. So you keep on moving from place to place. And radioactivity is a continuous process, okay, in the sense that it will not stop, but the beam itself is not continuous. So you have to be very patient to do this experiment, because the emission of an alpha particle is a stochastic, a probabilistic process. You don't know when the next one will be emitted, and that fellow has to be scattered. So you wait patiently till you accumulate enough number of scattered particles in all directions. So this experiment might have taken months or a year or whatever. That is what you do. And then you see whether you can infer anything about the structure of the gold atom. This was the great experiment that Rutherford did. So much so that apparently at some point somebody made a remark that Rutherford was lucky to ride the crest of a wave. There was a big wave and he was on the top of it and he became a famous man. But actual reality is what Rutherford himself told in response to that. He said, "I made the wave." This experiment he conceived, and there were his students Geiger and Marsden, who did even more careful observations, and he was able to build a beautiful picture out of the scattering, and that is what is important for us. So what I will do is, I will stop at this particular point. In the next lecture, I am going to discuss what the results of the Rutherford experiment are, and I am going to try to work out, not completely rigorously, but to the extent possible, I will try to work out whether the plum pudding model will be able to explain it or a planetary model will be able to explain it. I will argue in the favor of planetary model, and then we will see the Rutherford model is going to give rise to even more problems. Every time you solve a problem, it is giving rise to more problems. We saw that with the de Broglie wave. We are going to see that, and that is when the Bohr model comes to the fore. So we will stop at this particular point. We will meet tomorrow.